You guys talking about the problem set? Okay. Hello. How are we doing over here? Good? Decent? Medium? Terrible? Good? Okay. Okay. Let's see. Yeah, somebody noted I did not post to Gradescope the problem set. I apologize. I'm an absent-minded professor, but I will go post it right after class, and then I think I'll give you an extra day and turn it in sometime tomorrow. And there's still the grace period that I always put on there also. It goes to like Monday, but apologies for that. Thank you for letting me know. In general, if you see something like that, just email me and be like, hello, Gradescope, and I'll be like, oh crap, sorry. So that's good. What else are we doing? Any other logistical nonsense we need to worry about? I keep forgetting, I forgot on Wednesday to mention Annie's study group Wednesday night. So I'm hoping people are going to those. Or I guess, although she said something like Monday next week, I'll try to like pay attention and remind you guys. All right, so today I wanted to talk about partial derivatives. I want to start chapter 14, start talking about partials. And actually, let me look at, here's a function, okay? So this is a notebook I posted on. Here's a Mathematica notebook, and here's some pictures we're gonna look at. I don't know if we'll get to the most important image today, maybe we will. But here's a function, x cubed minus 5xy squared plus 3y minus 4. I don't know off the top of my head what that looks like, but here's a picture of it. Here's a picture of the graph. I think I did only from 0 to 3, x and y are only between 0 and 3. So I just wanted some kind of weird graph that we wouldn't be able to like predict the shape of just offhand, right? So this is a graph. And I want to think about, we want to start thinking about calculus, right? We've been sort of putting that off for a while, building up some facility with surfaces and with vectors, because those are what's going to be important here. So let me actually, hard to go back and forth, but so let me just write this function down and let's start thinking about it. So x cubed, let's see, so begin calculus. We haven't done any calculus yet in this course. So let's do some calculus. So here's a function of two variables. What does it say? X cubed minus 5xy squared plus 3y minus 4. And what if I want to know something about how the function's changing near a point? And so let's look at this function near the point 2, 1. Okay. And yeah, here's a picture of the graph. And if I look from above, I think that makes x horizontal and y vertical. 2, 1 is over 2 up 1. It's I don't know if you can see where my mouse is pointing, but anyways, so it's at some point on this graph. But I want to think about this a little bit conceptually first, like, and then what is something like instantaneous rate of change? Let's consider rates of change because that's what calculus is all about. And what I've mentioned, I think I mentioned the first day of class that like there's going to be this thing called the directional derivative. So it's like we could head away from the point 2, 1 in some direction. And seeing myself on screen is definitely not desirable. Okay, we can head away from 2, 1 in some direction, and then we could ask, what's the rate of change in that direction? So we could pick a vector as a direction to head away from. Pick a vector direction. Head away from 2, 1 in that direction and ask for the instantaneous rate of change. This is called the directional derivative. So it'd be the directional derivative of f at the point 2, 1 in the direction of the vector u. But we'll get to that. We're actually not going to go fully general yet. But for today, let's just focus on if you went like in the positive x direction or the positive y direction. Okay. We'll get to the fully general picture, but for today, focus on positive x direction. So if I call this vector, maybe if I use the vector u right here, then this would be u equals I. And positive y direction. So that would be in the direction of j. Right, those are kind of interchangeable. Okay. Now, how can we start thinking about the positive x and positive y direction, like what just moving in those directions? Well, one reason those are nice is because we have cross sections. So if I go back to the screen and think about, let's see, what information do I need here? Let's do the slice in the x direction. Actually, sorry, I've got a million things here that in this is going to be, some of this is going to look very strange until I actually plot it. But let me actually get rid of the. So if we take, this is a specific slice of the graph. Can you guys see that orange? This is a specific slice, and it's the slice when y equals 1. Right? We'll actually talk about, there's this thing called parametric, well, we actually will talk about parametric curves later on in the semester, because if you want to think about curves in 3D space, you have to give them, you basically just describe all the points. If you remember, if you ever did any parametric curves, we'll go through it. We'll go deep into parametric curves later, but that's how I was able to plot this. I don't know, this just looks kind of funny here, but if I overlay it with the graph, you can really see it lies right in the surface, right? So let's consider, so if we want the positive x direction, let's consider the slice, consider the cross section y equals 1. Okay, so the cross section y equals 1. So right, that fixes y to be a specific value and then lets x change, right? So x can change, y fixed, x changes. And I'm looking at the point 2, 1, so that's the slice I want. Okay, well, we can actually think about that. We can actually think about the function plugging in 1. I plug in 1, I get x cubed minus 5x plus 3 minus 4, like that. Is that fair? And this is sort of z equals, it's basically what we're plotting, that orange curve. And the picture is basically plotting like y equals 1 and z equals this simultaneously, so that you just get that orange curve. But what's nice about this, it's a function of one variable. And we know how to deal with functions of one variable, right? So we could call this like g of x or something like that, just as a function of one variable. So what's the slope at x equals 2? What do we do? What do we compute? The derivative, right? So the slope at x equals 2 is g prime of 2. And we can find g prime of x here. I think it's 3x squared minus 5. And so then g prime of 2 is actually 3 times 4, 12 minus 5, which is 7. And so that's actually the slope at that point. If you do go look at the picture, you can at least tell that it's maybe that it's around this point. And it does seem to be sloped upward at least. So at least we're in the z-axis is a different scale than the x and y axes, which is why it looks different. So, okay, this number right here is called the partial x derivative at that point, of this function at that point. So this is called the partial x derivative of f at the point 2, 1. Okay, so that's not too hard to actually compute. That's actually, it's funny. It's like, the reason why just setting y equals constant is nice, because it gives us a function of one variable and we can picture it nicely and everything. Okay, so what if you do the same thing in the positive y direction? You guys should be able to do this. Take a minute and see if you can figure out what the slope is at the same point, 2, 1, in the positive y direction. So now we're fixing x equals 2, right? Yeah, take a minute and see if you can figure it out. If you just do the analogous thing. Here I plotted it in blue on the graph. What happens when you plug x equals 2 in? So you might ask yourself whether you're expecting a positive or a negative number. It's a little bit hard to see the axes sometimes. guys do this. So what's the function here? What'd you guys get? Somebody tell me what they got. Plugging in x equals 2. Somebody's talking, but I can't tell who. Yeah. Minus 10y squared plus 3y plus, I didn't hear you, 4. Oh yeah, because you plug in the 2 and you get 8 minus 4. Okay, good. Actually, you can tell here, oh, I didn't even simplify it. I just kind of plugged in directly, but you can actually tell that that's the same. It's basically what I'm plotting is that function. Okay, good. So then what happens? And so if you call this like, this could be like h of x or something, right? So the slope we want is what? In terms of h. So h prime of 1. So, oops, not x, y, right? Sorry. So minus 20y plus 3. And so what did you guys get for the derivative? Negative 17, looks right to me, plugging in 1 there, good. Good, and so that's the partial y. Oh, okay. All right, so yeah, so let me just write a few things about this. So it's really just the derivatives in each of those directions, so that's easy enough. And if you think about it, these were the partials at a specific point, just like these are the derivatives at a specific, like this was a derivative at a point, but this is the general derivative, right? So we can actually do the same thing. We can have a general partial x and a general partial y, and then just plug in the point to find the specific number. So let me leave this function on the board here so we can refer to it. So if you think about it, sort of the more general partial x, if we want to just think about the derivative in the positive x direction at a general point, well, what we did is we plugged in a specific constant for y, right? So like the partial x in general, the idea is treat y as a constant. The idea is treat y as a constant in the expression for the function and then differentiate x. And then differentiate with respect to x. With respect to x. WRT is with respect to. So what do I mean here is if we treat this like a constant, if we treat y as a constant here, then what do we get? By the way, the notation is f sub x. Well, that's one notation. I'll talk about some of the notations. F sub x is, so we differentiate with respect to x. So x cubed becomes 3x squared. If we treat y as a constant here, what is this term? What does this expression become? If when we differentiate. So we're gonna pretend that we're just pretending this is a constant. So what do you do when you pretend something's a constant? Like it's minus 5y squared. It turns out to be, right. It's basically constant times x is what you're differentiated. So you get minus 5y squared plus, and then what happens to the 3y? If y is treated as a constant, what happens to constants when you differentiate them? 0, yeah, so plus 0. And so this is actually just called the partial x, like this is the general partial x. And we could check plugging in 2, 1, that we get the same number that we got up there, right? So now, yeah, so we're just treating like, yeah, we're just treating y as a constant. So like 3y is quote unquote constant. So that's why it becomes 0. And so then, so that's the general partial x. You know, it's not even at this point, it's just in general. And then at 2, 1, I mean, really, I should put like x, y here. It's a function, right? It's like f prime of x, but it's a function of x and y. So fx 2, 1 is 3 times 2 squared minus 5 times 1 squared, which is 7, which agrees with what we had up there. Right? So that's the thing. You don't have to actually go to the, you don't actually have to go to the trouble of plugging in the slice and then figuring out the derivative. You can just do the general partial and plug in the point, and you get the same number. Is that fair? And then for the partial y in general, you do the same thing. Because in effect, that's what we're doing, right? Plug in y equals constant up here was like, it would just be for different y's. Every point we chose, that's what we would be doing. Same idea. So what is f sub y in general? If we take this in different respect to y, what happens to the x cubed? Goes away, good. So then the minus 5xy squared becomes negative 10xy. You guys got the hang very quickly. Plus 3. Okay. So we treat x as a constant. Yeah, treat x as constant. Okay, and then at 2, 1, just to check that we got the same thing, we get negative 10 times 2 times 1 plus 3, which is negative 17. Get the same thing. Oh, sorry, with respect to. Yeah, that's just a standard. I just don't want to write out with respect to. Sorry, there's some specific ones like s dot t is always such that. WRT is always with respect to. KITCP is King is the coolest professor. No. Sorry. It's very standard. Everyone uses it. Okay. Ridiculous. All right. Okay, so that's the idea. And kind of, so there's this partial x, partial y. There's a couple things here like worth saying. It becomes, I mean, like, I think section 14.2 is like partial derivatives algebraically. And it really becomes almost trivial to like just to differentiate and integrate. No, sorry, not integrate. We have to integrations later. Differentiate because you're just differentiating like you normally would. You're just treating the other variables as constants. And by the way, maybe that's worth saying like we can even do the same thing for like functions of 3 variables or more. There is a limit definition if you want to give it. I mean, it's kind of like I could give you. Actually, yeah, maybe I'll say 2 things. So the limit definition, if you just want to kind of like the formal definition, So recall, f prime of x for a function of one variable is you do that limit something like this. That look familiar? It's like the change in the function over the change in x. You could, this h is like a delta x as, and you let the change in x go to 0. Yeah. Well, the idea is it's an instantaneous rate of change. So x is changing and y is fixed. And so it's really what we're talking about is the instantaneous rate of change in the x direction. Yeah, because we're fixing y and then letting x change. You're right, I probably should have written that down, but like that's what the partial x means. It's like, it's the instantaneous rate of change in the x direction. So if you recall, this is like the limit definition of the derivative. You could think of this as delta x if you prefer. F of x plus, maybe I should change these to delta x actually, because I think it probably will be more evocative when I go to the two variable case. So this is like delta x goes to 0, delta x here, delta x there, right? And so you basically, this is like an average rate of change. This is basically delta y over delta x as x goes to 0, as delta x goes to 0. Right? That's what this really is, the delta y. Because if y is f of x, that's how y is changing as x changes. Right? Okay, so if we want to generalize for f sub x, if z is a function of x and y, I guess I should say if y equals f of x, then f prime of x is that. If z is a function of x and y, f sub x, the partial x, is the instantaneous rate of change as x changes in y and is fixed. Instantaneous. Guess I could add ROC here to rate of change. It's another acronym. IROC has instantaneous rate of change. As x changes, y is fixed. And so you could write this down. You could give a limit definition if you'd like. It's actually, again, a limit as delta x goes to 0 because y is fixed, and you just do something like this. You don't change the y. Right? It's just kind of like, that's the derivative in the x direction. The y is fixed, and then the y doesn't change with the x changes. Does that make sense? And you could probably imagine what the partial y is. It's very similar. It's just, I'm going to change y and fix x. So x, y plus delta y minus f of x comma y all over delta y. So these numerators are both changes in z, but they're kind of different changes of z, right? This is some specific change in z only when you move in the positive x direction. And this is a specific change in y, change in z as you move in the positive y direction. We won't use the limit definition too much. It's just nice to think about a little bit. That's like the analog. This also gives us a different notation. Like we use f sub x and f sub y I should talk about other notations. If you remember, we had different notations for the derivative, right? We had f prime, but we also had dy dx or df dx, you know? So in general, we can think about, again, maybe I'll give the analog with the single variable derivative. I stopped the share a long time ago, right? Okay, good. Okay, so other notation, or I should just call it the Leibniz notation because that's what it is. Leibniz notation. So again, recall that f prime of x by definition is the limit as delta x goes to 0 of delta y over delta x. And that in this limit, we just write dy over dx. That's where the notation comes from, right? Just thinking of it that way. And it's almost like you can think of dx and dy both being 0. Like this is one of those indeterminate forms, right? It's 0 over 0 as delta x actually goes to 0. And a lot of times when I think about dy over dx, I think of it as like dx is something like impossibly tiny. And dy is the corresponding change in y. If you make a change, an insanely tiny change in x. So then what we do is f sub x is the limit as delta x goes to 0 of delta z over delta x. And so what we write, although we write something different here, let me just say both of these. We want to distinguish from the single variable case and distinguish that this has something to do with like the variable matters. So instead of d, we use this scripty, this like scripty d, this like fancy cursive d, I don't know. Doesn't even look like a d really. So we write dz or dx or dz dy, but we have to use a different kind of d to indicate that this is a function. This isn't a full derivative. Like dz over dx with standard d's would mean it's the derivative of z with respect to x, where z is just a function of x. But here, because there's multiple variables to differentiate respect to, we need to somehow indicate that. Yeah. Why don't we just write dz dx like this? I think it's just to indicate that there's other variables. So you have to think about other variables. So like this doesn't represent the full range. Yeah, there's even a sense of like what a total, there's even a question like what is a total derivative, but that somehow this is not right. This is not the rate of change, the entire rate of change. Like it's not the whole story about the rate of change. Like there's other things going on. And so this is kind of called, so we don't write this. This is called a partial. I mean, people write like partial z over partial. That's not a useful partial. So people say like partial z, partial x, or. And in the math typesetting language, LaTeX, where we write our nice math, which I really should give you guys the opportunity to use sometimes if you want. You make all the fancy math with these commands, backslash commands, and it's backslash partial makes this characters. So yeah, these are what we use. So if you'll start to see these around, and it just looks a little different from the standard D. Okay. Yeah, those are the main notations. I mean, you'll also see, sometimes you'll see something like, Other notations, sometimes you'll see something like f sub x is like d sub x of f. Just to indicate that it's like the derivative with respect to x. This is less frequent, but there are other books and other people who use something like this. Okay. I did want to mention also that like you can do partials for functions of 3 variables. Another example, like what if I had f of x comma y comma z is x times y squared times z cubed plus sine of x xy. Start to make life a little bit harder for you. There's a partial x, a partial y, and a partial z now. Let's do another one. ln of y z squared. Let's make life harder. Let's think about what the partial x would be. Yeah, this is like constant times x, right? So this is just the y squared z cubed. Sine of xy, differentiating, pretend y is a constant and x is variable, yeah. Yeah, it's like sine of 5x or something like that, right? Which pops out the constant in front times cosine. You remember your chain rule? Plus y cosine xy. And now this one doesn't have a x in it. That's 0. Try the partial y and the partial z. Give you guys a minute to do it. Check in with your neighbors. Compare notes. I didn't put a product rule in here. So I wanted to be really mean. I could have made it like y sine xy or something like that. Let's see if we remember calculus. Check with your neighbors if you think you have answers. See if you guys got the same thing. Or talk it out. Get answers here. Chain rule. What's the shaking of the head?
No, that was just a wake up.
Oh. Unless she also was shaking her head. Oh my God, yeah. Sorry. Thank you. 2xyz cubed plus I did the easy part. Yeah, right, okay. What happens with this one with respect to y? It's kind of the same idea, right? X cosine xy. And there's no z there. Now this is fun. You guys remember your sorry, say again. It's z squared. That's derivative of the inside. What's the derivative of ln? 1 over. So it's 1 over all of this. It does. It does. And something similar happens here. What's the numerator? 2yz over yz squared. Yeah, it's a chain rule, right? So it's 1 over blah times the derivative of blah. And so 1 over yz squared times z squared. Now, there's a little bit of a trick why the z didn't matter here and the y doesn't matter here. I gave this kind of on purpose. You remember any fancy log rules? What's the log of a product? So this is actually ln of y plus ln of z squared. And actually you can pull the 2 out there. So this is actually ln of y plus 2 ln z. And so that's why this you just get 1 over y and this you get 2 over z. So it works out either way. You don't have to remember the fancy log rule, but that's kind of why that's z, because actually these really are separate. Like they don't really influence each other as far as derivatives go. Little calculus reminiscing. It's fun, right? So yeah, so this is the idea, and it's not too bad. I guess maybe one other thing worth doing. I do want to, based on Monday, we're going to start talking about tangent planes and stuff. Are there any questions about anything on there, by the way? Yeah, please. The ln of yz squared. Well, the derivative of ln of blah is 1 over blah times blah prime times 0 blah, right? So that's all I'm doing. I'm just using the chain rule on. When I teach math 1600, I actually do a lot of this blah, like writing blah stuff. Yeah, I mean, the derivative is that, right? 1 over blah times, that's what the chain rule says. It's the derivative of the outside. The outside is the natural log. So the derivative of natural log is 1 over, and then times the derivative of the inside. And so that's what these are. Like this yz squared is just what's inside. And then when you differentiate yz squared with respect to y, you just get z squared. Good. Bless you. So I do want to talk, by the way, Mathematica will do this stuff too. Like, so back to the screen, like this function that we were looking at, it will actually compute partials. This command basically says do the derivative with respect to x. And this says do the derivative with respect to y. And so we get the two things we got before is the partial x and y. And I guess there's some stuff here. Okay, yeah, 7, and we got negative 17 there. Okay, and then maybe just a couple quick pictures, and then we'll go. I do want to say one other thing, but just when I'm going with some of this stuff is we're going to eventually start looking at tangent planes. And in particular, if I look at this picture, I can add in actually the tangent line to the blue, like the green is the tangent line to the blue curve, right? And so you actually can think about the tangent line there. You can think about the tangent line. I have this red line tangent to the orange curve. And if you plot, well, there's a plane there that contains basically the green line and the red line. I think I have a picture that'll work for all of it. So this gets to be a little bit busy, but the blue and the orange are inside the surface. I have a weird, like, I don't know what it is, like aphasia or something, where it's like I look at one color and I say another, so we have to be really careful. So the blue and the orange are in the surface. The red and the green are tangent, and they actually form, those two lines form this plane, right? These two lines determine this plane, which is called the tangent plane. And now it's a little weird because it goes through the surface in other places and stuff, but that happens with tangent lines too. If the curve curves back in the other direction, you can have the tangent line pass through the curve again, right? But we're going to start talking about tangent planes. And somehow, if we want to think about what the entire derivative is at a point, it's really like somehow given by this tangent plane. And so we're going to get to the formula for tangent planes pretty soon. That's 14.3. And then just to think about conceptually, this is a problem from the book, which is sort of like, if you want to think about partial derivatives in tangent planes, I'm sorry, what am I saying? Partial derivatives in contour maps. So this is a contour map of some surface. And you could ask yourself like about the sign of the partials, like at Q. What's the sign of partial x? Well, this is going through height 15. And that is probably height 16. I think that's 17. So that's probably height 16. So if I leave this point going the positive x direction, I'm going up, right? 15 to 16. So that's actually a positive. So the partial x at that point is positive. But if I go from this point and head in the positive y direction, that's going from height 15 to height 14, I think. So in that case, the partial y is negative. So at this point, partial x is positive, partial y is negative. I think you can look at like at this point, I think both partials are negative. Up at that top right point, both partials are positive. So you can sort of start, you can look at pictures of contour graphs and sort of just say like the sign of a partial derivative at a point, often just by sort of seeing what's the other contour it's heading towards. And then I think we're out of time, but what I was going to do here is you can actually estimate partial derivatives also. Like say we're at this point, 2, 2. This is actually a plane, so you can get the exact partial derivative. Like if I'm at height 6, and if I go over 2 units, I'm at height 10. So what's the change in z from this point to this point? 4, and the change in x is 2. So 4 over 2 is 2, would be like the partial x. And you can do something similar here. You go up 1 unit, you go down 4. So the change in z is -4, the change in y is 1. So I think the partial y is -4 in that case. But sorry, so kind of ran out of time. But that's the idea, and they'll give you some homework, I think, for, I guess it'll be for like next Friday on this stuff. But all right. we'll stop there and call it a day. Have a good weekend. I do have office hours now, and also I will be in my office at 2:30 this afternoon. A few of you emailed me about if you can meet this afternoon, so I will be in my office from 2:30 on. If you want to stop, sorry, I didn't reply to all the emails yet, but if you want to come this afternoon, and thanks for telling me about